Alright, hello, welcome to our project. We're calculating the moment of inertia with two methods. So we're gonna change the moment of inertia and we're gonna have a collision, and during this we're gonna assume that it's a torque-free environment.
Okay, here you can see this is our first method. He's jumping on and it spins. It's a collision. Whoa.
So we're trying to calculate the moment of inertia of the carousel. So what we have to do is use a momentum lens because we know that it's a collision between two bodies with no outside torques. So we know the initial angular momentum. So we know the initial angular momentum of Evan is equivalent to the final angular momentum of the system. So to calculate Evan's initial momentum, we know that he's a point mass, and because he's hitting the carousel tangential to the radius, the perpendicular radius is the same thing as the radius. So we know that the angular momentum of a point mass is equal to the mass times the velocity times the perpendicular radius. But since the perpendicular radius is just the radius, it's just MVR. Okay. So that's the initial one. And now as we go to the final one, we know the final angular momentum is equivalent to omega times the sum of the moments of inertia. So the carousel's moment of inertia as well as Evan's moment of inertia. We know Evan is also a point mass. So we know Evan's moment of inertia is mr squared. So we know from here that the angular momentum, the total energy, or the total angular momentum of the system equals omega times the moment of inertia of the carousel plus the mass of Evan times the radius squared. So that's the perpendicular radius, which is also the same as the radius, which is 4/5 meters. So from here, we know that the velocity is approximately 1.25 meters per second that we got from our tracker data. And so from here, we can say that the the angular momentum of Evan, which is the initial angular momentum of the system, is equivalent to the final angular momentum of the system, which is the angular momentum of both Evan as well as the carousel. And that's equivalent to MVR, which is 70 kilograms for Evan's mass, times the velocity, which is 5/4 meters per second, times the radius, which is 4/5. I like that because it cancels out. Okay, so we know omega. We travel 2 pi radians for one rotation. And for us, it took approximately 5 seconds for one rotation. But we want the rotations on top so these units cancel. So we get radians per second, which are the units of omega, or 1/2 because radians don't have units. So we get omega equals 2 pi over 5 seconds. Come over here and we plug that into this equation. So we know 2 pi over 5 seconds times moment of inertia of the carousel plus 70 kilograms, which is the mass of Evan.
Oh my gosh. It's because the critical
This is an R, not a B. Yep. Times the radius, which is meters squared. So we have that equation. So isolating the moment of inertia of the carousel, we get that 170 over pi, which is this thing simplified, multiplied by 5/2 pi. And that's kilograms meters squared. Subtracted from this, which is this section. And we got, this is about 54, this is about 44, so we get about 10. So we get the moment of inertia of the carousel is about 10 kilograms meters squared.
Okay, this is our second method. He's spinning, spinning. And he's gonna move in, decreasing his moment of inertia, and it's gonna spin faster. Sweet.
Using our second method, then we will be changing the moment of inertia of the system by moving towards the center of the carousel. And then this will allow us to solve for the constant, which is the moment of inertia of the carousel, rather than the entire system. And so our initial conditions was I stood at the edge of the carousel at a radius of approximately 4/5 of a meter. I then moved towards the center, while the idea was to get at the actual center, we got only a rough approximation of that, and it is about 1/5 of a meter. So now when we solve for this, we're going to be using angular momentum, L. And we know that since this is a torque-free environment, the initial angular momentum has to equal the final angular momentum. And we can find this using the formula for that. The initial inertia followed by angular velocity has to equal the final angular momentum, angular velocity times the final moment of inertia. And so, while these will be values we measure from the video, these will be two derived values. And so, the values we got from the video was omega final and omega initial equal 2 pi over 5, and then 2 pi over 2. And so the reason we got these, or how we found these, was by measuring a full rotation and approximately how many seconds that took. And so 2 pi, a full rotation, initially took 5 seconds, and upon changing the moment of inertia, it changed to then 2 seconds. And so then now, when we solve for this, it's going to be the inertia, initial moment of inertia is going to be the constant of the carousel. So IC plus myself, moment of inertia, IE. And so the initial values of that times the initial angular velocity has to equal then the final angular velocity times IC, the moment of inertia of the carousel, still a constant, plus then my new final moment of inertia. And so we can then set this up to be a ratio, because that's what's going to happen. When we change our moment of inertia, we're then changing the velocity by a ratio. So we'll set this up to equal initial over final equals then these two over each other, moving that there and that there. So W final, or omega final over omega initial, which then equals 2 pi over 2 over 2 pi over 5, which then equals 2 pi 2 pi, which then gives us a ratio of 5 over 2. And so now we know that this ratio will equal 5 over 2, and we can now solve for our constant. So we're going to rewrite this below.
So on the interval, -2 to 2, this function, dx, will at hypertext.
So we have here the initial and the final, and we're now going to insert our ratio, and again moving that 2 back on over, and the 5 here. And so this is our 5 over 2 ratio, and we just move them back to the respective sides. And so what we're going to do now is plug in our values for my moment of inertia. So initially, we know that's going to equal mr squared in both occasions. And while my mass of 70 kilograms does not change, we know that our radius does. So our radius initially was 4/5 of a meter, squared. And this gives us 70 times 4/5. So we're going to leave it in fraction form.
Oh, I really screwed it.
And this is kilogram meter squared. And that equals our initial, my individual initial moment of inertia. And then our final, my final individual moment of inertia is still going to be 70 kilograms. But now we're at a much smaller radius, 1/5. Which gives us our new final moment of inertia, which is going to be 70 times 1/25 kilogram meters per second squared. Kilogram meters squared. And so now we're going to plug these values, which we solve for here and here, back into our equation we found before.
You are, but you're not using that equation. You're using like the whole concept.
And so now what we're going to do is distribute the 2 and the 5 to each of their respective sides, and then solve for our constant.
So he did an extensive thing class, kind of showing
And so we got this 32 over 25 by then just taking 4 squared, 16, times 2, which gives us 32, over then 5 squared, 25. Kilogram meter squared. And then here, we just have 1 over 25 times 70 kilogram meter squared. Excuse me, that 5 was distributed there. And we're just going to have 70 times 1/5 kilogram meters squared. And so what we're going to do then is subtract 2 of the constant from both sides, and then subtract this value, 70 times 1/5 kilogram meters squared, from that side and this side, and that will then allow us to solve our constant. So we have 3 of the moment of inertia for the carousel's constant is equal to this value. And so this comes out to be 75.6 kilogram meters squared. And so now we know this value equals 3 of our constant. So if we just divide both by 3, it ends up our constant being, let's give this a little space, 25.2 kilogram meters squared.
In a short summary, we did 2 methods to determine the moment of inertia. We did the changing the moment of inertia and a collision, and we got about 25.2 kilogram meters squared for this one, and about 10 kilogram meters squared for this one. And you're probably wondering, why are they so different? Well, we assumed that it's in a frictionless environment, but since it actually wasn't a frictionless environment, that will create the change, because we know that the work done by friction equals the force of friction times the distance. And since we calculated this one over a longer distance, because it took multiple rotations, there's more friction that's changing the momentum than this one.
Thank you for watching. Hope you enjoyed the video. Make sure to like and subscribe, and please give us an A.
I'm gonna run and jump right there in between that and you jump. I'm gonna try and get like that. We'll try and get like that. Yeah. And then just try and like move ourselves in like that. Yeah. See, that was fast. Holy shit.